was just demonstrating the food chain, and some large animals, not blue whale, will eat very large fish, which eat medium-sized fish, which eat small fish, okay? And which eat small crustacean, which eat plankton or so. So when the food chain is really long, not as much of the energy in the food gets from here to here. Because each time, and these are like arbitrary numbers that are reasonable, that just illustrate the concept. If you start out with 10,000 units of energy, all right, each time you move up, you lose about 9/10 of the energy. And so only about 1/10 of the energy is passed along each step of the food chain. So if you start with 10,000 units of energy, then you have 1,000 at the first step, 100 at the next step, 10 units of energy at the next step, 1 unit of energy. And if this large animal then ate a large fish, in its ecosystem that was like 10,000 units of energy, it's only getting 1 unit of energy. Does that make sense? So on a shorter food chain, there's less decrease in the energy. If we start out with the plankton here, and then we go to the krill, which is what we saw the blue whale feeding on, then there's still 100 units of energy there. And so if this very large animal can go down to the place where there's still a lot of energy left, he skips all of these decreases in energy steps, then he gets more of what is available. And since the krill do tend to go in these big patches and swim together, then all he has to do is open his mouth and he gets dinner. And so the largest animals on Earth that have ever been on Earth eat these small krill. Krill are kind of like shrimp, but they're in a different order. Anyway, they're pretty different, but they kind of look like shrimp. And this is usually they're in the cold seas, like the Antarctic. And the whales go down there to feed. And so this allows them to eat a lot of something very small. So how do they do that? These are the baleen whales. Okay, this is a baleen plate. So the plates here this is the baleen. So each of these, it hangs down in plates from like the front of the mouth. They're like pages in a book. And so these are all baleen plates. And you can see that they're long on the outside, not so long in the middle. They're long on the outside. Here's its tongue, so this is looking at it face on. Oh, is that true? No. Well, no. Sorry, this is the front. And so it's kind of cut at a slight angle. So opens his mouth, a bunch of water comes in, and all the krill where it chose to feed, and then closes his mouth, the tongue pushes up, pushes all the water out, the water goes through the baleen plates, and what happens? All the food stays. It works as a sieve. The baleen plates work as a sieve, and the tangled fibrous mat, if you will, allows the krill to stay and to be swallowed. And so that's how he feeds. So this is an example of a suspension feeder. I'm only giving you one example. There's another example of fish, various fish. Suspension feeding is mainly aquatic. Why is that? because the water suspends things. Okay, we can't just go around opening our mouths in the air, right? And ingesting food because there's not a whole lot there to ingest.
What terrestrial animals does that apply to? Would you say mainly water?
I can't think of any. You don't see birds doing that either. So let's just call it aquatic. There's probably an exception somewhere, right? Just showing. All right. So, 3 types of main feeding mechanisms: attack of individual prey items, suspension feeding, and the baleen whale is our example. And now we'll look at association with symbiotic microbes. You probably know this example, usually biology 102 or 201, or anyway, you're beginning biology 211. What is it here? 200, okay. You usually talk about these in the ecosystem. And that's the coral, the reef-building corals, and their symbiotic relationship with algae. Symbiotic means what? What was it?
Together and mutual.
Together. So it's beneficial for both. It's beneficial for the coral, it's beneficial for the algae to have this relationship. And so what happens is the coral provides the housing, and the algae live inside the coral, okay, within within the coral. And what the algae do then, so the coral's the landlords, right? Gives them a place to live, but they have to pay rent. And their rent is that the algae are photosynthesizing algae, and so they get energy, they use energy from the sun to build carbohydrates, and they pay the landlord, the corals, some of these nutrients. They use some for themselves, but they share with the coral. And so it's a relationship that is beneficial for both. One provides housing, the other provides nutrients in payment. And here it shows you the algae just under the epidermis where they can get light. Okay? Can anything go wrong with this system? So sometimes the algae leave under certain circumstances, and so then the coral looks bleached out because they're not dead yet, they don't die immediately. They can survive for a while, but they are becoming in a very unhealthy state. And some of the things that can cause bleaching, anybody?
Changing temperature.
Changing temperature, either an increase in temperature or a decrease in temperature can cause bleaching. So human activities like something that's increasing turbidity, all right, so then they can't get the sun, the algae can't get the sun, and they would die. Let's see, some other ideas, maybe the changing in pH levels, carbon dioxide. We worry about global warming, that this is going to have a big effect on the coral reefs. And coral reefs provide habitat to like 25% of marine species. So pretty important place to focus. So change in light or nutrients changes, they can stress out the corals. Again, if they're bleached, they're not dead, the algae can come back, but the circumstances need to be changed or they will not survive. So, our big example of symbiotic relationships. And now we move into digestion. So, attack of, you have to locate the prey, you have to identify it as prey, and then you ingest it. And after ingestion, for most of us, not for the sea stars, well, they do ingest it eventually, but they ingest it already broken down. So after ingestion, then we need to digest. Digestion is breaking down molecules breaking down nutrient molecules. So nutrients, as we saw at the beginning of this chapter, include the proteins, the carbohydrates, the lipids, even includes nucleic acids and minerals. And those are broken down inside. So for us, we have the stomach, and that's where we release enzymes, and well, that's where we start to release enzymes, and that's where foodstuffs start to be broken down. That continues into the small intestines, and we release more enzymes, and we finish breaking them down in the intestines then, the small intestines, eventually into individual monomers. This happens in the small intestines in most animals. In the monomers, what's a carbohydrate monomer? The monosaccharides. Monosaccharides, that's like glucose, saccharides. Okay. Protein, it's a monomer, amino acids, and then the nucleic acids, A, C, G, T, or U, some of the nucleic acids. That's digestion. Taking the big carbohydrate molecules, such as starch for us, and breaking it down to its monosaccharides, or the big proteins that we ingest, and breaking it down to the amino acids, and taking the nucleic acids to the individual units, and breaking down lipids into the fatty acids, or glycerol, fatty acids and glycerol. That's digestion. So for all of us, almost all animals, we digest these with enzymes. So we release enzymes into the stomach to attack proteins, and then once it gets to the small intestines, then we release enzymes, lipases that attack lipids and carbohydrates. Even in our mouth, we release enzymes that start of attacking carbohydrates. And so most all animals do this breaking down with enzymes that break the links between the molecules that make up the large protein or carbohydrate. So here, we're looking at fermenters. Fermenters also digest with enzymes, but they also use a symbiotic relationship with microbes. And let me step back one step. We all, in our guts, us and all the rest of the animals, we pretty much have a gut microbiome. So microbiome, uh-oh. I know how to fix it now. Okay. I don't know why they're here. This is not good. Okay, I know how to fix it.
Done.
All right. I forgot where I was. All right. So all of us have a gut microbiome. And this microbiome are bacteria, fungi, mainly bacteria, yeast, even some archaea, they're thinking now. And these help us with digestive processes. And that is exemplified by the fermenters. So we have foregut fermenters and we have hindgut fermenters. The microbes are usually in a very enlarged structure, and in the ruminants, which are foregut fermenters, it's this very large structure called the rumen. And it's not pictured here, but there are 4 other parts of the stomach that basically start right here by the esophagus. And that's the reticulum, the omasum, and the abomasum. And so this is one place that food goes, and it's the first place that food goes when a ruminant, such as a cow, eats food. And these are called fermenters because it is anaerobic here, as it is in our guts. And they break down, these microbes that live here are anaerobic, and they're able to break down foodstuffs. Specifically, they break down, so this is a symbiotic relationship, they break down foodstuffs that the cow, or a different type of ruminant, cannot break down on its own. So what they do, in the cow, this is cellulose. So cellulose they're linked together differently than like starches, and we cannot break these down. Cows cannot break this down by themselves, but the bacteria can break these down. And they break them down into what they call short-chain fatty acids, 3 or 4 carbons long. And these short-chain fatty acids then can be absorbed. So wherever they're broken down, and here it's in the big rumen, they can be absorbed through the lining of the rumen directly into the body, or they can travel along through what's not shown here, the reticulum and the omasum and the abomasum. And they can travel that direction to the small intestines where there's a lot of absorption of the short-chain fatty acids. So the The cow provides a place for these microbes to live, very much like the symbiotic coral and algae. And then the algae can break down something that the cow can't use, which is what grass is basically made of, the cellulose stuff, into something, short chain fatty acids, that the cow can then absorb and use. So that's one thing that it does. The other thing that these bacteria can do is they synthesize vitamin E. Sorry, I meant to say B vitamins. And we don't do a good job at that. They can synthesize B vitamins. And the third thing they can do is that they can take a waste product, urea, which can enter the rumen from the blood, and they can take it and break it down and use the nitrogen to build amino acids. We can't do that. Neither can the cow by itself. Urea is a waste product that we excrete in the urine, but we're excreting all this nitrogen. And so what the bacteria does is allows this nitrogen to be recycled. It takes the nitrogen from the urea, breaks it down, and builds amino acids. And then, when the food passes through the reticulum, neomesum, abomesum, into the small intestines, then these amino acids are absorbed into the animal. And so it's a really nice system. So who are the ruminants? I'll just name some ruminants. And you know these because you know about Artiodactyla. These are basic. Many of the Artiodactyla are ruminants. And that includes the sheep, the antelopes, cows, goats, camelids, moose, deer, giraffes, buffaloes are all ruminants. And other foregut fermenters include the kangaroo, hippos, colobus monkeys, sloths. So there's a lot of different animals, including animals that are considered ruminants, that do this. But what they need is a large expanded space for the microbes to enter or to live in. And this has to be, it can't be real acidic, so it's not like our stomach. Our stomach is what pH when we eat? Anybody? Really low, about pH of 2, okay? The rumen is nothing like that. It's a little bit acidic, but it's maybe 6 point something. It's much closer to neutral, and that's where the microbes thrive and do their job. And then when all this is mixed, then it brings up the cud and rechews it into smaller. And then when they swallow again, this is diverted into the reticulum, abomesum, mesum, to the small intestines. So, with fermenters, it works best if you have always some old food that the mixed food, the new food can mix with. And that way the microbes are constantly mixed and able to grow. And then when the food is sent down the other way, well, some microbes are going to go with it, but you still have left a nice healthy environment for lots of microbes that stay there. All right. So the ruminants always have the stomach of several compartments. big thing here, short chain fatty acids, synthesis of B vitamins, and amino acids, all of which, when they get to the small intestine, gets to be absorbed. So again, here is the function of the gut microfilters. All right, so those are the foregut. The foregut is the stomach. The midgut is the small intestines. That might be helpful. So the foregut is the stomach, basically. The midgut is the small intestines. And the hindgut is the cecum and the large intestines. So we have here then the foregut, the midgut, and the hindgut. So then there are animals that are hindgut fermenters. And remember, in the foregut fermenters, the fermentation occurs here, and then after it's broken down into short chain fatty acids, after the B vitamins are synthesized, after that amino acids are synthesized, it goes through the midgut where it can be absorbed into the body. So taking from the tube and moving into the body itself, that's absorption. And so that really works nicely with the foregut fermenters. But what about the hindgut fermenters? They have a stomach very much. Oh, you know what? I want to tell you one more thing about the ruminants. So in one of your presentations, I don't remember who was presenting, you talked about the stomach of like whales, and that they have 3 or 4 stomachs also. And they do something similar. They're not called ruminants, okay? But they have a microbe community that ferments in their first stomach, in their foregut. But what it ferments is not cellulose like the ruminants do. Any ideas? Chitin. Breaks down chitin. Okay, so very similar, not a ruminant, but a very similar stomach. I mean, they're both artiodactyl, right? And so, similar setup to break down an undigestible item. In the case of the whales, chitin. All right, back to the hindgut fermenters. So here we have digestion, and again we have the enzymes here and the enzymes here. But any cellulose goes right on through, does not get broken down until here. We have this expanded cecum. So we have a tiny cecum, but it's not very big. It sticks off of the large intestines right at the entry of the small intestines into the large intestine. And so that's the cecum, and then it heads out the large intestine. Well, like in the rabbit, it has a very large cecum. And a pony is another hindgut fermenter, and it has a very large colon or large intestine. So two different structures that are enlarged, but these are both called hindgut fermenters. And other examples of hindgut fermenters would be, besides the rabbit and horses, that'd be the zebras, the rhinos, the apes, the elephants, the koalas, some rodents, and some of the big birds, especially like geese and grouse, chickens even, and some lizards. So these are hindgut fermenters. They're doing fermentation here. Again, it's not acidic here. And their microbiome does similar things. It breaks down into short chain fatty acids, which can be absorbed. Right? So just like the foregut fermenters, in the hindgut fermenters, they can absorb in the cecum and the large intestine the short chain fatty acids. But the gut microbiome in the hindgut fermenters, they also synthesize B vitamins, and they convert waste nitrogen and urea to amino acids. But they can't absorb these. So they can't get the benefit of the B vitamins. They just pass out into the feces. And they can't get the benefit of nitrogen. But almost all hindgut fermenters have solved this problem, and the idea is they eat their feces. Okay? And when they do that, then they get these B vitamins and the nitrogen amino acids. Horses do that. Rabbits do that. Rabbits actually kind of separate their feces. They have a soft feces and then the pellets. And the pellets are the waste material. The soft feces contain these items, so they know what to eat. You just eat the good stuff. So very similar. It's just how they obtain the B vitamins and the amino acids that the microbes synthesize. They obtain that differently. Anything else I wanted to tell you? No? All right. So this is showing what process? Digestion or absorption? This is showing digestion. Digestion is the breakdown. So these are the enzymes that break down amino acids into smaller parts. And once we get into these small chains, then there will be other enzymes that break down into the protein monomers, which are amino acids. So these are just different amino acids here. So at first, in a very large convoluted protein that lands in the stomach, the acid, the pH of 2, what's the importance of that acid with these proteins? Think about it. Denature. What does denature mean? Denaturing proteins. What does that mean? It means going from its exact three-dimensional shape into its chain of amino acids. So it breaks all these bonds that hold this in this functional protein shape. This is denaturing, and this is what the acid does. That allows the enzymes to come in here and attack. And each different type of enzyme attacks between specific or groups of specific amino acids. And so it breaks them into chunks, and this is what occurs in the stomach. And then, when the food moves through into the small intestines, then we start breaking them up into the individual amino acids by enzymes that are in the small intestines. Again, this is going to happen in all animals, including the hindgut fermenters, the foregut fermenters. They're all going to be breaking these down. And then it's the individual amino acids that can be absorbed through the epithelium of the gut into the body and into the bloodstream, where these are sent directly to the liver in a portal system. Monosaccharides, very similar. Again, the carbohydrates such as starch are going to be broken down into the individual monosaccharides. So this is showing, what process is this showing? Absorption. This is absorption. This is taking from the lumen of the gut to the inside of the cell, through the cell, and into the bloodstream. It's not showing that, but into the bloodstream to leave, to go to the liver, because the liver then processes both the amino acids and the carbohydrate monomers. So this is only showing carbohydrates, but it's very, very similar for amino acids. You don't need to know these exact names. This is GLUT5, GLUT2. This just means that it's a glucose transporter. Or, as you can see here, fructose, the different amino acids. And they might have slightly different transporters. And then this is, I can't remember what SGLT stands for. And I'm blanking on it right now. But it can have co-transporters with sodium that's always wanting in. And so it can bring in glucose and galactose. Or there are some transporters that can do this. And then on the other side of the cell, they have to be transported again. Again, the active, this is consistent throughout the body. The active part of absorption is kicking the sodium out and bringing the potassium in, the sodium, potassium, ATPase. You've seen this over and over in the kidney, in the gills, etc. This is active, and then everything else happens. So secondary active transport, or facilitated transport, where we have a protein but we don't have to expend energy. And we get these, including the amino acids. This is how they move across the cell. And then they move into the vein and go directly to the liver in the portal system, the hepatic portal system. So again, only showing carbohydrates, but this is how proteins are absorbed also. So this is the lumen of the intestine, and then this is the cells, so this is the body. And we have these microvilli. The importance of the microvilli is that they increase the surface area of the gut, and they also have the blood vessels to carry away the nutrients to the liver. Those are the main purposes of these villi. Fats are very different in how they are absorbed. What do you think is the main reason that it's so different? what are fats in relation to water that amino acids and carbohydrates are different? Amino acids and carbohydrates are hydrophilic. They like water, they dissolve in water. Fats are hydrophobic. And that makes all the difference in absorption. Because with these hydrophilic molecules, you know that this is a lipid bilayer. They cannot get through that lipid bilayer. They have to have proteins to enter, both the amino acids and the carbohydrates. But fats, they don't like to be in the watery environment of the lumen. They clump up. How far do we want to get into this? Oh, wow, it's time. They clump up, but we have bile salts here to make them small clumps, okay, of fatty acids. These fatty acids then are delivered, these are called micelles, and we'll start the next class with this. Delivered to the membrane, and then the fatty acids go right through. No problem. And we'll talk about this next time. So we'll have our last presentations on Friday. We'll finish digestion and we will begin a little bit in reproduction again. So quickly, I have a question. Would you rather look at female reproduction system, male reproduction system, or general reproduction ideas? General, we'll start at the start then of yeah.